Cool, let's make a start. So today's class we're going to be getting into the exponentials and logarithms chapter section. For this one in particular, we're just going to be looking at how we can solve exponentials and how we can graph exponentials. This will be something that you do in both Unit 1 and 2 and Unit 3, 4, so it'll be relevant to everyone involved. Cool, okay, so solving exponentials, what's going on here? There are three main techniques that you'll be using to solve exponential equations. We're going to go through all the main ways in which you can solve them. The most common of which is going to be probably using option 3 here, using a logarithm. That'll show up a lot in your extended response style questions, the tech active. And then the other two are more so for your tech-free type stuff. But let's see what's going on. Okay, first approach, equating exponents. We saw a very similar thing when we were doing polynomials, where if we had two polynomials that looked identical, more or less, they had the same sort of format, you could directly compare the coefficients of each of them to each other, and therefore solve the polynomial coefficients. Very similar here. Our goal is to take our exponential, and this usually only works for simpler exponential equations, and try to rewrite them in a way where the left-hand side is directly comparable to the right-hand side. Like for instance, we have our 3 to the power of x is equal to 27. If you're able to identify that 27 has a base of 3, it's essentially just 3 cubed there, we now can see that these are very similar looking expressions. They both have a base of 3 and they both have some power. One of the powers is x, one of the powers is 3. It's not a big leap in logic to say, okay, the left-hand side should therefore have an x equals 3 for these to be equivalent. So essentially what we're trying to do using this approach is to rewrite any exponentials in our equation to share a common base and any other constants as well. We try to write them in exponent form. As long as everything shares a common base, they can then be directly compared. You equate the exponents together and you solve for whatever the unknown is. This is a pretty simple version of the approach. Any questions as to how that works so far? Easy. Here's a more difficult version. So you have two exponentials as opposed to just an exponential and a constant, and the exponent, the index itself, is also a bit more complicated. Again, we're just going to make sure they have the same base. 25 has a common base of 5, it's just 5 squared. We use a bit of our index laws to simplify this. So as a reminder, when you have what I refer to as cascaded powers, so you can see this is 5 squared and then to the power of minus x plus 2, the way that one works is you multiply the powers through. From there, we can see they both have a base of 5 and they both have some exponent. From that point onwards, we don't care about what the base is. The only thing that's left over is what's in the exponents. And well, that's just linear, so there's nothing too complicated there once you get to this stage. Anything to clarify there? Because part of this will require you to understand your index laws decently enough. All good so far? Cool. Okay, so the next approach up is the quadratic solution to exponentials. You'll typically use this for more involved exponential equations, like this one here, for instance. You've got 3 to the power of 2x plus 6 times 3 to the power of x. There's a whole bunch of stuff going on in there. It's not immediately obvious how you might get them all into the same base and directly comparing them to each other. The other thing that messes this up a bit is coefficient. Right? Like for instance, if we just do a really basic example, if you have 3 to the power of x equals 3, then it's pretty obvious that x is going to be 1. But as soon as you chuck a coefficient on the exponential term, you can't really compare these two things anymore because, well, this coefficient exists, but there isn't one that's equivalent on the other side anymore. They're no longer similar enough to directly compare. If you just chuck in x equals 1 here and pretend that this didn't exist, then, well, you get a stupid solution of 6 equals 3. Not great. So that's a bit about like why we need a slightly different approach to solve these kinds of questions. There's a couple of ways to identify when to do this new approach. We'll get into that in a bit more detail, but the really baseline thing to watch out for is just, hey, if it looks complicated, you're probably going to be using this approach that we're about to see. That's the really basic way of looking at it. So here are the steps. Let's have a look. First things first, we want to make sure all of the exponential terms specifically share a common base, very similar to before. In this case, you can see they both have a base of 3. They're both 3 to the power of something. If you don't have that, then you want to use your index laws to try and create that. This is where things differ. We want to try and rewrite this in a way where it looks like a quadratic. So the way to essentially do that is to identify some sort of substitution where you end up with something that looks like a quadratic, a squared plus 6a minus 27. The way you do that is you look for the simplest exponential in your sequence. Now remember, they should all have the same base, so you want to pick the one that's the most fundamental of the lot, right? This is just basic old 3 to the power of x. This is 3 to the power of 2x. I would consider that to be the simplest substitution. So all I'm simply going to do is replace every instance of 3 to the power of x with a. You can go straight from here to here if you like, if you're already familiar with how that would work, right? Like all I'm doing here is replacing that with an a and this one with an a squared because that's 2x. If that's sort of complicated to see how I got from here to here, then what you can do is you can use your index laws a little bit here, where you can essentially take this a step further and not only get them to the same bases, but also get them to look exactly the same exponentials as well. So you can see this is 3 to the x, this is also 3 to the x. You're just taking that 2 and using the index laws, you're knocking it off. That makes it a lot more clearer as to why we can do that substitution in that way. That's the hardest part of this. So I guess I'll just pulse check real quick. Are we all good with how that's worked? Nice. This is now just a quadratic. Solve it as you please for any other quadratic methods. In this case, I'm just using factorization. And it's going to get us 2 separate solutions, a equals -9 and a equals 3. The challenge here is we're not trying to solve for a, we're trying to solve for x. So now that we know that a is equal to these things, we can now replace a with what it actually is, which is 3 to the power of x, and then just say, okay, a is -9, sure. That means that 3 to the power of x is equal to -9. Same thing over here with the other equation. This gets it into the simple form that we saw earlier, and so all we do now is solve them in whatever way we like, whether it be equating exponents or whether it be later on using logarithms. The only possible solution here is x equals 1, and that's going to come from 3 to the power of x is equal to 3. There is no solution to this thing, right? There is nothing you could put in the power of 3 to the power of x such that it would end up equaling -9. We'll explore that in a bit more detail as we look at the graph of things, but just as a very basic touch on it, this is the basic graph of an exponential. The base here, you can a base of 3 and a base of 2 are more or less the same thing for the purposes of this discussion. Just basically, this graph is entirely positive. There is no possible x value for which you're going to get a negative number. So for that reason, there is no solution to that. You only look at the one where you can have solutions to. Clear enough so far? Okay. So, beyond just sort of looking at complexity, when should we be using quadratic solutions to these things? One of the easiest things you can look for are descending coefficients of x. So you can see this one has a 2x, this one has a 1x, and this one you can think of as having a no x, right? So that descending power down from 2 to 1 to 0, that's very quadratic-like, x squared plus x plus constant. It's not always going to be exactly like that, or at least it's not going to feel like that. Sometimes you might need to simplify further. Like for instance here, you have what doesn't look like descending powers of x yet until you get the base in the same base as the other exponential. So you convert this 9 into 3 squared, and now we see that we have 2x, 1x, and no x. In fact, I've even gone a step further and split off this plus 2, again using index laws. So this bit here turns into this. Whenever there's the plus there, you can essentially distribute it into two separate terms, and all I've done then is combine that into the coefficient. Now you can clearly see your descending powers of x's there. That's the main thing to look for, that sort of ratio. The other thing that's pretty simple to look for would be the coefficients that are directly on an exponential. We kind of touched on that earlier. As soon as you have a coefficient on your exponential, there's not much else you can really do unless it can be converted into the constant, like divided onto the other side, for instance. But, you know, if there's all this other stuff going on in there as well, that's very unlikely to happen. So that's the other thing to look for. Fair enough so far. Cool. So we haven't looked at logarithms yet. I'll touch on this anyway, just to get you an idea, because you guys might have looked at it yourselves at some point during school. Shouldn't be too relevant for the questions we're going to be doing today, but it's worth just looking at anyway. So, logarithm solution. How do you work with it in this sort of scenario? Again, this is useful for exponentials that are simpler in nature. We just have 5e to the power of x is equal to 4. First thing you want to do here is get the exponential on its own. So just divide everything by 5. Nice and easy. From there, there is a specific conversion you can do. We won't get into too many specifics on exactly what that looks like, but essentially what you're doing is rearranging each of the terms in the equation to get the x on its own. What you'll see in the next couple of weeks will be the relationship between exponentials and logarithms and how you can convert between the two. I'm only really showing you this just to show you that this will be something we have a look at some point, and you can see how quick it is to do. Right, so you have a question like this, it only takes you like 1 or 2 lines to get it to a stage where you've solved it. And this statement here would be considered the exact solution to it. You don't actually go any further. That just is what it is. This is going to get more complicated because we need more logarithm stuff. So we will have a look at that in a later class. Cool. Okay, so in summary, these are the main things. Oh, no, just these, I guess. The equating exponents approach and the quadratic solution approach. Next up will be a bit of graphing, but before I get into that, happy to take any questions for clarifications. If you think of one, you can also put it in the chat as well and I'll go back into it, or even just hop off mute, however you like. Okay, so graphing exponentials. What's going on here? Hang on, we've got a question maybe. Can we do a practice question using the quadratic method? Definitely will. Yeah, why not? Let's do that now. Let's take a break from me talking a lot. Practice question with the quadratic method. There's the sketching. Cool. Okay, so something like 4a would be the quadratic method. I'm immediately able to spot that because I'm noticing like there's a 2x, there's a 1x, there's a no x. 2x, x, nothing. Some of them are a bit more complicated because I got coefficients in other spots, but they haven't done anything super crazy just yet. It's still very easy to spot the descending powers of x there. So that's one way you would know. Something like this might end up being one, but definitely these. So let's give this one a shot. So what I'll do is I'll transfer over to the handwritten notes section. I'll start writing it down. Let's see how we go. Three power of 2x minus 2, 3 to the x minus 3 equals 0. I think I got that right. 3 to the 2x minus 2, 3 to the x minus 3 equals 0. Yes. Cool. All right. Who wants to take a stab at what we might do first? I'll also leave the procedure up on the screen share as well. How would we do step one here? Cool. So step one says make sure that all of the exponentials share a common base. The base of an exponential is the thing that is being raised to the power of. So step one, you'll have to do it usually in most exam or SAT cases because they want to test your understanding of things. In this case, they already both have the same base of 3. So there's nothing actually to be done here, but more so applicable to when you get when you get it into the exam or SAC. So yeah, no worries. Step 1 is already done for us. Step 2 is convert to the quadratic form, which I can appreciate probably sounds a bit challenging just by looking at the wording. So maybe what I'll do is I'll show what that actually looks like from here on. A very similar question, actually. Let's see if we can get it. Anyone want to take a stab at what that might look like? We're going to be doing a substitution of some sort. In this case, we substituted a equals 3 to the power of x in the screen share version. Why have we done that? And is that applicable here, perhaps?
I rewrote the equation as 3x squared
Yep.
minus 2 times 3x.
Mm-hmm.
Oh, sorry, yep, 3 to the power of x minus 3 equals 0.
Yeah, that's good. It's a nice little intermediary step to make life a little bit easier, like exactly
Yep.
what this substitution would look like.
And then just replace the 3 to the power of x with a. So you would get a squared minus 2a minus 3 equals 3. A equals 0.
Yeah, no, that's perfect. Fun fact, this replacing of a technically isn't necessary. You can, if you really wanted to, just go straight into 3 to the power of x's and solve it like it's a quadratic anyway. This is purely and simply just for us to read this better. This doesn't actually need to happen, it's just a legibility thing. But yeah, we got a quadratic now, which is nice. What do we do to now solve it?
Factorize it.
Yeah,
So then that
factorize
would
it.
be a minus 3 times a plus 1.
It's 3 and a plus 1. Mm-hmm. Cool.
So a could be 3 or negative 1.
Yep, a equals 3 or a equals negative 1. Nice. That got us all the way through step 3, which is nice. Almost there.
But the only valid one here would be 3 to the power of x equals 3 because you couldn't have 3 to the power of x equal to negative 1.
That's right. Yeah. 3 to the power of x. There's no value that would make this equal to -1. So we ignore that one entirely. And now this one has a pretty nice and easy solution, which is
1.
yeah, x equals 1. Perfect. Could also be worth exploring a bit about like why. Like I did show you the graph that has no negative numbers. So let's sort of explore it just by sort of plugging in values. If you imagine choosing bigger and bigger exponents, all you're essentially doing is making this number bigger. Like 3 squared gets you to 9, 3 cubed gets you to 27. As that number gets bigger and bigger, you're only making yet another bigger number entirely. And as you choose numbers closer and closer to 0, like let's say a half, for instance, any fractional indexes are actually some form of root. So for instance, 3 to the power of a half would actually be the square root of 3. And what we're essentially doing now is getting closer and closer to 0, because square root of 3 is going to get you, what, like 1.7-ish, maybe? Hard to kind of estimate these things. But as that root gets bigger and bigger, you now take more and more drastic roots, which can only ever get closer and closer to 0. And the last thing that can happen is what happens if I now choose negative numbers. So 3 to the power of -1. Well, the way that one works is maybe before I explain it, does anyone remember what negative indexes do to a number?
Would it be 1 on, then like in this case, 3 to the power of 1?
Yeah, precisely. You just flip it. And what you can imagine is if this got bigger and bigger, well, that just means you have a really, really big denominator. And so again, you're getting closer and closer to 0. And so yeah, for that reason, none of these ever get to none of these are ever getting to 0. Oh, sorry, no, ever getting to negatives. You're only getting closer, approaching 0, but never actually crossing over to the other side. That isn't, of course, unless you literally chuck a negative on your exponential, then obviously that's going to make the whole thing negative now, instead of the whole thing being positive. Yeah, that's pretty much it. That's how we apply that type of solution. Do we need to have a look at another one like that, or are you happy enough with how that works?
Can we do maybe like a harder example? Because I can imagine like a scenario where the numbers in the experience would make it a bit harder to use this method.
Yeah, okay. So worth pointing out, this is the Unit 3-4 book, and this is as hard as the book is giving. Let's see if they do in the chapter review bit. No, that's the same thing there. Still just 2x, 1x, no x. This is just getting a bit more drastic. You can see this is now going to be a cubic instead. You've got 3x, 2x, 1x, no x. And that brings us back to like our polynomial methods now. You're starting to use factor theorem and that sort of thing. But it's still very much the same. That will be a long example. It's kind of rare as well. I think the next closest, it's not really showing it here. You know what? I did have an example to make things more complicated in my notes. Maybe I'll just do that one and we won't show the solution and we'll just do it live. Because that had a few things going for it. To the power of x minus 2 times 3 to the x plus 2 plus 81. There's a few other things to now worry about from here. I'll pull back up the procedure, should we wish to follow it. A lot of the complexity differences are going to happen pretty much at the front of the question. Once you get to like even past step 2, actually, everything just sort of devolves back into solving a quadratic and then going from there. The challenge is going to be in your step 1 and during step 2. Step 1 wants us to make sure all exponentials share a common base. The first question you've got to ask yourself is, do they currently share a common base? And if not, what could we do?
I think you'd have to change the 9, maybe using like the square root, or I'm not sure what it would look like though.
Yeah, okay. So basically, what you're doing by comparing, yes, you do have to change the 9, you're right. You need to think about the factors of 9, essentially, and then figure out from that what power would I have to raise one of those factors to make it work. Because that's pretty much the bulk of it. You're breaking down the factors until they become prime factors, and then from there, what multiple of those factors will get us up there. 9's a pretty easy one. You've got 9, you've got 1, and you've got 3. Those are your only options. Only one of those can be raised to a power to get back to 9.
Or would you just do inside brackets 3 squared and then just to the power of x?
Yeah, that's exactly right. Yeah. And then we could also do something here, but maybe we'll just keep it simple for now and just do one change at a time. One of the cool things here is because of the index law being that these multiply together to simplify, well, one of the fun things you can do is actually just flip the order entirely. You could do 3 to the x and then square it, because it's still just 2 times x versus x times 2. They mean the same thing. That way, the reason why we would prefer to do it this way is because if you have a look at like the other examples, for instance, we wanted to have it like basic 3 to the x. But yep, so that's that one. This one's also kind of, yeah, we do need to do something with this. Once the screen focuses, of course. This will test your index law stuff again. I'll write out, so we're already sorted with this. We need to figure out what we can do about this. Maybe to make life easier, I'll also pull up the notes on index laws so you can see what your options are for simplifying it. Okay, cool. There's a big summary of all your options. It's going to be any of those options 1 through 4. Even if you don't know what's going to happen at the end, if you could just pick out what index law seems like it should be the one to use, I'll take that as well.
Number 1.
Number 1, that's right. Do you know what that's going to look like? Or do you just see the similarities?
It would just be 3 to the power of x times 3 squared.
Yeah, that's right. Awesome. So the reason why index law 1 is going to work is because basically you look at the thing you have, which is it has a base and it's raised to a power where there's an addition in that power. You would then look in your either your mental library or your actual formula sheet and be like, oh yeah, this is also a thing that has a base raised to a power with pluses, so I should be able to replace it with the other side since these are equal, essentially splitting that plus up into 2 separate things. Nice. That's pretty much the bulk of the effort there. There is a bit of tidying up that could be done, but we're pretty much at the stage where we've got our 3 to the x, which is what we want. Any other simplifications we would do before our substitution?
Would you square the 3 to make it 9 and then times it by the 2? So it would be negative 18 times 3 to the power of x.
Sounds pretty good to me, yeah. Negative 18, 3 to the x, and then yeah. Perfect. Alright, this has got it back to the stage where we were previously. Happy to follow this one all the way to the end if you like. Otherwise we could move on. Let me know.
We can just substitute it in now. So
yep.
We could just be a squared minus 18. And then a again. 18a plus 81 equals 0.
That's it, yeah. It's a bit nastier of a quadratic, but you're still able to solve it the same sort of way. Actually, that wasn't too bad. This one even can be factorized as well.
I think it's a perfect square.
Yeah, I think so too.
Yeah, a minus 9 squared equals 0.
That's right. A minus 9 all squared equals 0, because 9 9s get you the 81, and then minus 9 gets you the minus 18. And yeah, might as well just bring it home. Why not? What else we got?
A equals 9.
A equals 9, which then tells us, because we've got to solve for x still.
Oh, sorry. Okay, yeah. We get the 3 to the power of x equals 9, so x equals equal to 2.
Yeah, that's right. So the other stage that you did in your head was knowing that 9 is just 3 squared, and then realizing that, well, x is equal to 2 there. If you square 3, you get to 9. Perfect. Yeah, that's gonna be the hardest this'll get. This was Unit 3-4. So in a tech-free environment, if this is easy enough, or if you're at least seeing how this would work and would be able to practice it yourself at this stage, then congratulations, you will knock these ones out pretty much every time. Because even on exams, this is exactly what they end up looking like. This will actually be harder, I would say, because I try to chuck in everything I could to make it weirder, which is converting base, doing a few weird index law stuff. Usually you get something like what we saw in the textbook earlier, which is, well, nicer to hear, because it means it'll be a bit easier for you in the actual thing. Cool. I mean, since we're already on the point, I don't think there's anything else to really look at for solving quadratics, because what you do in the quadratic solution is kind of the same as what you're doing in the other approach as well, because at the very end of the quadratic solution you are eventually using equating exponents. So unless you want to have a look at another quadratic solution thing, that'll about wrap it up for solving. Thoughts? Happy to move on to graphing at this point. Cool. Okay, so graphing. We saw this before. This is what the basic exponential looks like. It's a bit of a funky graph. It has an asymptote, horizontal asymptote to it, and the way because the x is in the power and because you're changing the variable being the power change, essentially means as x is increasing linearly, you get an exponential increase. Like for every increase of x, you get a much more drastic increase in y. Like 2 squared gets you to 4, but then just going from 2 to 3 gets you all the way to 2, 4, 8. So, gets a bit more drastic. The other strange thing about exponentials is that you don't just have the dilation, translation, and reflections to worry about. the base of the exponential now also has a bit of a significant impact to it. It's less about what the number actually is and more about what range of values it falls in. Like for instance, what you're seeing here is the basic shape of any exponential with a base that's greater than 1. It'll just look like that. And you can see here, like with 10 to the power of x, right, it's basically just the same thing. It's only going to determine how drastically it shoots up, how drastically it's going to either increase up to its maximum values or decrease down to 0, the speed at which it does that. The more interesting thing is that when you have a base between 0 and 1, we're effectively having a flip across the y-axis. So this is essentially a reflection in the y. The reason why is because we kind of touched on it earlier, which is when you have a fraction to a power, raising that power is only going to raise the denominator bigger and bigger. So as your x increases, or in essence as you go right on the x-axis, we can see the y values are decreasing over time. And this is also what we had a look at before, which is if you now start doing negative numbers, that negative index is just flipping your fraction, which is why as you go left, you're now increasing your y values, because you're flipping that fraction to becoming an integer and then raising that to a power. So you're achieving the opposite effect and effectively achieving a reflection across the y-axis without actually putting a negative sign up in the power. Clear enough why it's doing that? Yeah, a lot of how graphs work, you'll be able to determine literally by just testing some numbers, like testing some negatives, testing some positives, testing 0, see what actually happens to the numbers, and that'll get you a rough idea of what the shape will end up looking like. So if you get into your more complicated extended response style questions and you get a weird looking graph, even just testing a few points to get the gist of what's happening to the y values can be quite nice to know. But okay, so we still have the other factors to worry about. Dilation factors work the same as they always have. If you have a multiplier at the front, you're essentially just stretching it along the y-axis or from the x-axis. And yeah, you can see the effect is a lot less drastic than if you had changed the power. If you had changed the base, rather. But they both more or less do a very similar thing, which is just making it shoot up faster or slower, depending on if you choose your factor differently. You also have dilations along the x or from the y. If the number gets bigger, you shoot up faster. If the denominator gets bigger, you then shoot across the x-axis for longer. Reflections. So now that we have issues with the base of our exponential, we now need to have essentially two separate pictures to figure out what happens if a reflection occurs. So we've got our base between 0 and 1, base between 0 and 1 down here, and basically any other base that's positive. Basic, if your base is positive, it'll typically look like that, so putting a negative sign at the front will now flip it across the x-axis like we were already expected to do. But obviously if your graph normally looks like that, putting a negative sign on the front will now make it go down again this way. So in both cases you're flipping the green across the x-axis. It's just a matter of what the green actually looks like initially. Cool so far on that? I know there's a lot to take in for this sort of stuff, so I'll drop the notes in the chat as well, so if your notes are still falling behind you can copy back off of that. Okay, cool. And then reflections in the y-axis, those are always denoted by having a negative directly attached to the x. And so one of the funny things is because you can already get a reflection in the y-axis by being a base between 0 and 1, you're now flipping it back to, in this case, the blue line, which would look like this green line. You're kind of flipping things back and forth. In fact, you can even see the relationship between bases, where essentially if one is the negative reciprocal, so 1 over the other one, the flip of that will be identical to if you had just said 2 to the power of x. So said otherwise, those two, oh, I can't draw a box across the whole thing. Bugger. Basically 2 to the power of x is literally the exact same thing as a half to the power of negative x. Those are identical. Translations. So horizontal translations, yes, they shifted horizontally. When you're actually graphing things, you don't really care about them. They just sort of happen to be there as part of your solution. They don't really change a whole lot as for how you actually draw the shape of your thing. It works the same as any other function, where if you have x plus a number, you're shifting it left. If you have x minus a number, you're shifting it right. Remember, we're dealing with functions rather than transformations here. So we're back in function land, where things are a bit backwards for x. Vertical translations is the more important term, because shifting the whole thing up reveals the asymptote as a key feature that you now have to document. So normally you have an asymptote at y equals 0. This is as you get closer and closer to 0. When you put a +1 on there, even though this exponential term is getting closer and closer to 0, because you're always adding 1 to it, it now makes the new asymptote at y equals 1. That's a bit of the math as to why that's happening. In reality, you just got to think about, it's normally just an exponential at 0, I'm shifting it up by 1, now it's an exponential at y equals 1 instead. Same thing for vertical translations that go downwards as well. One of the things we're starting to see is that exponentials may or may not have all of the like x-intercepts and y-intercepts. Like for instance, if you have a look at this blue f of x, this doesn't have an x-intercept at all. And so depending on how complicated your exponential is, you may not even have to find a whole lot of key terms. This one, for instance, you would just have to figure out what the asymptote is, which you can just read off of that. The y-intercept, which is just x equals 0, and that's literally it. Other than, like, you know, the overall shape, like does it go up and right, does it go up and left, so on and so forth. Yeah, when it comes to actually solving x-intercepts, it usually is a complicated endeavor. You have to start using logarithms, which is why they typically don't do anything with it until after you've learned logarithms. This looks complicated. It's not that bad, trust me. This is me going like, this is the most complicated it could possibly look, where you've got all the transformation factors in there. But okay, what do you actually care about? The horizontal asymptote, for one, always given by the vertical translation. We saw that here, right? This is -1, so that is -1. X-intercept pretty much is never going to be this complicated. You're probably just going to be using, where is it? This, if it's pre-logarithms. If it's post-logarithms, again, it'll only actually look like this, where you do line 1, line 2, line 3. So it won't be that bad. At least for now. And y-intercept, x equals 0, very simple. So if you just think about the generic exponential here, shoving an x equals 0 here, a lot of the time that just is what you end up with. You just replace one thing with 0, and then, well, that's what you have. That's the answer. We'll have a look at what this looks like in an example. It'll be a bit easier that way. So here's all the steps you have to hit. Let's have a look at them. I've made this nasty because if you can handle this one, you can handle the nicer ones. First step for pretty much... Did I hear someone off mute, or was that a question? I might just be hearing things. Anyway, so the first thing you would want to do in pretty much any graphing scenario is to make sure what you're looking at actually looks like a graph that you know. This is a hot mess of numbers. Kind of hard to see what's going on. Not too hard, but, you know, you'd rather make it a bit nicer. So distributing that -3 through everything makes things a bit nicer. And if you want to go above and beyond, you could also go ahead and reveal what the true horizontal translation is as well, by taking that coefficient off of the x. But we kind of talked about this earlier, where, at least for this type of graph, exponentials, horizontal translation doesn't really help us a whole lot. So you don't really have to do this bit, but it's good practice for your other functions which do require it. This is like a global. You can always do this for functions. Taking the coefficient off of the x will reveal the horizontal translation for any of the functions you'll look at. Easiest thing to now do is look at the vertical translation, and that will therefore give you what your asymptote should be. There's a +1 here, so we're going to have y equals 1. Nice and easy. Next up, we're going to be identifying the shape by looking for any possible reflection terms. Now, that's going to be any negative signs either on the x or on the y, respectively, but it's also going to be based on what is the base of the exponential, if it's between 0 and 1, or if it's any other number greater than 1. You may or may not have seen the letter e before. E is kind of like pi. It's a special irrational number. It's roughly 2.7-ish. The only thing you really need to know is that it's bigger than 1. And so for that reason, it would normally be this graph. A number bigger than 1 would look like that for the base. Up and to the right. But because we have this negative sign, we now have to flip it down and to the right instead. So, looking at a combination of the base and the reflection terms will get us a rough idea of what the overall shape should look like. That's probably the hardest part of exponentials. There's two ways things can reflect. So I'll just do a quick pulse check here. Are we clear enough with why that's happened in the end? Cool. Okay. Next up, axes intercepts. So the same as always, y equals 0 for x intercepts and x equals 0 for y intercepts. This is logarithms, so take it with a bit of a grain of salt for now. Basically, you sub in your y equals 0, get the exponential bit on its own, do a fancy conversion, and then from there it's just basic get x on its own at that point. You'll have a nasty looking answer, but yeah. Usually it'll be a lot easier before you look at the logarithm stuff. And this is what I was saying earlier. X equals 0 gets your y intercept. That's literally it. You just chuck in your x equals 0, and this can't be simplified any further as far as tech 3 is concerned. So these look complex, but that just is your number. one step. If you have endpoints, you'll watch out for those. We don't have endpoints in this case, we don't really care. And then we just plot out all the key features. X, y, and then once you have the x and y, it's kind of hard to mess up the shape. What is a bit complicated is because you have these nastier numbers, it's kind of hard to know, is that a positive or a negative? Like, you know, you got this -3 attached to the e. How do we know this +1 is so big that it's actually positive instead of negative? That's going to be the hardest stuff that you'll have to worry about. So the way to work with that is, first of all, knowing that e is roughly 2.7. Just think of it as a small positive number, if that helps easier. And you just kind of do a quick, it's basically a vibe check, right? It's like, how big is this number really going to be? You've got a small positive number raised to a big negative index, -6, right? So it's going to flip to 1 over that thing, and then it's going to have a big index on it. You basically got a number with a really big denominator that might as well be 0. And so putting a -3 on it, sure, it's going to flip to negative, but it's also pretty damn close to 0. So we can say that this essentially contributes nothing, which is what we saw here, right? You basically can't tell the difference between the asymptote and the function. And so for that reason, adding 1 to a really, really small number will basically be 1. That's the logic you follow. You only need to do this for one of the points, because as soon as you do it for 1, there's no other way you could draw the graph other than to put the other dash over on the right hand side. Because otherwise you'd have to draw your graph like this and then dip back over here, which would look kind of complicated for no reason. So you just follow your curve once you got one of the points good, and you'll pretty much never have a labeled axis, so you can put this wherever you feel like. If you do have a labeled axis, it's probably in tech active, in which case you just control enter on your CAS and you get the number that you need. Yeah, you pretty much never have to worry about endpoints. Pretty much always you'll have a maximal domain. If you don't, it's fine, just sub in the values like you always would. If you have to cut it off at -1 and 3, sub in x equals -1 and 3 into your function, and yeah, make sure you use the proper dots on them. Cool. Alright, anything to clarify from any of that? If not, we'll get into some questions and try to do some of the sketching. It won't look nearly as complicated as that, but as I said, if you can handle the most complicated stuff, then the easier stuff will be trivial. Cool. Alright, let's round out the rest of the class with... oh shit, where is it? I think it's at the start, isn't it? Chapter 5. Let's see. So we got some basic exponentials with not much on them, some dilation factors, some reflections, a bit of function notation stuff, some applications. Applications we'll look at later. Exponential applications can be really complicated to people. And then this one's actually a bit of a weird chapter. It has a little bit on sketching, and then the rest of it has nothing to do with exponentials. It's purely based on transformations. This could have been any function, and it might as well have been in the transformations chapter. So I guess the easiest one to start looking at would be stuff like in 5a. So let's give that one a shot. Y equals 2 to the power of x plus 1 minus 2. Yep, that one's written down. On the screen share, I'll have the procedure up, and you guys also have the PDF if you want to pull up your own copy of that as well. So, let's see if we can get a sketch going. And we'll see if my camera can focus. Come on. That's better. Alright, step 1. Rearrange to make sure we can clearly see all the key terms. Have we already got that? Do we need to do anything? As long as you can identify what all the key transformations in there are, we don't really need to do any rearranging. Does anyone know what the what transformations are present in the function? Maybe. Okay. So basically we have a horizontal translation because anything that's like additionally attached to the x, whether it's a plus or minus, whether it's a multiplier times, that's going to be your x type transformations. So x plus 1 in any other functions will always be a shift left by 1. And any time that you have either a plus or minus at the very end of a function, it could technically be out the front as well, but we usually don't see it there. Any plus or minus separating the functions, that's a vertical translation. In particular, this one will be shifted down by 2. So step 1's fine. We already know what everything is. Step 2, find the asymptote. Y equals c, where c is the vertical translation. Our asymptote, therefore, is what?
Is it just -2?
Yeah, -2 is correct. That's it. You're looking at this number, and yeah, -2. Dot. Cool. Alright, asymptote sorted. Next up is identifying the shape of the graph based on its reflection terms. So reminder that there's two things to worry about here. Easiest one is if there's any negative signs that are multiplying either the y or the x. Do we have any normal reflections in here? Any negative signs on the x or the y? Yeah, that's right. Cool. So there's no normal reflections like there would be in the other thing. Now, one of the things we now have to do is look at the base. This is the other issue with exponentials. So the base, there's two outcomes depending on which way it's going to look. What category do we fall into? I'll have it highlighted as well on the screen share.
Because the base is greater than 1, would it rise from left to right?
That's right, yeah. So we're going from right to... Wait, sorry, which one did you say?
Left to right?
Left to right.
Like
Yeah, left to right.
Yeah.
So we're going from left to right. That's, yeah. So we're going to have roughly this sort of shape. Now, when you're doing this, when you're sketching this out yourself, kind of do it a bit finely. You just want to know roughly what's the shape going to look like. And the reason why you would draw it finely at this stage is because it's kind of hard to tell how drastic of a curve this is going to be. Like, it could curve like that, or it could be really drastic like this. One of them has cuts through the bottom, one of them has cuts through the top. So just sort of eyeball it roughly and get a nice and smooth, easy to rub out sketch. And then once you actually solve what those key features are, then you'll be able to determine how drastic the curve actually was. Why not just do that at the end? Well, knowing what this curve looks like initially will tell you how much effort you have to put into solving it. Like for instance, if we determine that the curve is going to roughly look like this, I'm not going to bother looking for any x-intercepts because it's just not touching it. Whereas in this case, we're definitely touching whether it goes through here or here, so now I'm going to look for both. Yeah, that's pretty much it now. So we just got to solve for axes-intercepts the same way we do for any of the functions, at least initially, which is you're subbing in the x equals 0, y equals 0 stuff. That shouldn't be too complicated. What should we start with?
If you set x equal to 0, you got y equals 0.
Yeah, let's double check. So you're going to have 2 to the power of 0 plus 1. Yeah, looks like it. Y equals 2 minus 2, which of course is going to be 0. So actually we had none of those outcomes. It didn't go below or it didn't go above. It went dead center. Because if it cuts at y equals 0, the only way it can do that, I kind of missed it, but you get the point, is it has to go through the origin. So nicely enough, we don't even have to bother with the x-intercept because if you have a cut at y equals 0, you also cut at x equals 0. But just for the fun of it, why not? We'll show the proof. So you'd set your y equals 0. Whoops. You have 0 equals 2 to the power of x plus 1. Sorry, plus 2. Minus 2, rather.
And you get x equals 0 as well.
Yeah, you'll get x equals 0. That's right. You get 2 equals 2 to the x plus 1. This has an implied index of 1. 1 equals x plus 1. X equals 0. Which we kind of already knew from back here. Yeah, so we got x equals 0, we got y equals 0. There's no endpoints to speak of because there was no domain associated with it. If there was, let's say for instance we did 0 to 2, you would now just do that basically, where this would be your dot, your full circle, and whatever this y value is would be your open circle. And then yeah, step 6 is just sketch once you have all those things, which we already did. Cool. That was obviously one of the simpler ones, where the only thing that really mattered there was No, we did kind of look at a decent amount, which was getting your head around the reflection terms in conjunction with the base, as well as the vertical translation, which will set your asymptote. After that, everything else kind of just becomes x equals 0, y equals 0. Yeah, that's about it. If I just sort of go back to the textbook, there will be some reflection terms in there with negative signs. You'll see different bases. The only thing that's going to matter is if it's between 0 and 1. You'll see a bit of function notation. That's more transformation stuff though, so as long as you're familiar with that, you should be fine with those. And don't worry too much about the applications. Yeah, it's tech active, so you should be still fine with it, but I know they can get quite complicated. Cool. Alright, well that's solving and sketching of exponentials. I'm happy to stick around for any further questions if there are any. Otherwise, yeah, I'll leave you to it. Enjoy the rest of your day.
Thank you.
Thank you.
No worries.
Hi Chris, I wasn't here on Monday. I was just wondering what I missed.
On Monday? Yeah, good question. What did we do? Did we finish up? I think it was more polynomials. Yeah, factor theorem and remainder theorem. So we briefly touched on it at the end of the last time. We did polynomial division stuff. The recording of that will come out by tomorrow or so, I believe, along with this one, as well as so you can see what we're going to cover in the curriculums, either in the Math Methods Mastermind Premium module, the thing you can actually see the curriculum ahead of time. So probably easier than watching the full hour video would be to watch the relevant modules in the classroom instead. That'll be a bit faster for you, unless you want to see this sort of stuff, of course. But yeah.
Okay, cool.
Easy.
Awesome. Thank you, Chris.
No worries.
Bye.
Take care.
Bye.
Got a question for me? If you're talking, you're muted. No, he's AFK. Alright, I'll give him a minute to sort out any tech issues, if there are tech issues that are causing you not to talk. Otherwise, yeah, if you have the question, just send me a text or so. You've got the school text chat if you want to use that. And I think you might even have my number as well. Is he here? 30 seconds. Alright, now screw it. Text me if you need it.